Thank you. Good morning, everybody. Excuse me for my English accent, which is not very good. So the purpose of this presentation is a regressive approach in modular response analysis. This work has been realized in the laboratory of cancer bioinformatics and system biology of IRCM in Montpellier University. The team was composed of Jean-Pierre Borg, who is a PhD student, and Professor Jacques Collinge, who is the leader of the team. And Montpellier is a big city located in south of France, close to Marseille. So I'm going to speak about a specific model, which is modular response analysis. Modular response analysis is a mathematical method which unravels biological networks, and this method was developed firstly by Kolonenko in 2002. We will sum up the classical version of MRA, and we will extend this approach with the use of multiple linear regressions. We will test shrink-wave methods such as lasso, step forward, and step backward regression methods. And also we will examine two methods, least square estimation and regression with thresholds, that we name TLR. The main advantage of these linear regression methods is to be well adapted to sparse networks. So we will compare the performances in terms of sensitivity and specificity with two groups of examples. The first one comes from in silico map kinase network with 6 modules, which is a highly non-linear network. And the second one includes 2 sets of networks of a DWIM challenge 4. Biological network inference is a classic problem whose interest has increased because of reduction in the cost of experiments and of data acquisition methods more efficient. The dynamic of the system is governed by an ordinary differential equation, x dot equal fxp. X are the nodes of the networks, f is the kinetic function, which is a node, and p is a vector parameter. In the case of MRA, we can determine the gradient of a function f. Classic MRA consider the steady states, and we have x dot equals 0. We suppose the existence of a local solution at the baseline P0, and we note this local solution xP0. And thanks to a very important theorem, the function implicit theorem, we can write the activity of a node xi as a function of the activity of the other node xj. To obtain the regressive approach in modular response analysis, the main idea is to consider the Taylor development at the first order xi. And the variation of the activity of a node xi depends on the sum of contribution of the variation of the other nodes xj. The quadratic error is the vector parameter p, and the NO of this Taylor development is the derivative of xi in relation to xj. And these coefficients are very important, and we call this coefficient connectivity coefficient. So classic MRA goal is to infer biological network in a steady state. It means to compute the gradient of a kinetic f function. How to proceed for 3 nodes network, for example. We consider the baseline as a control state, and we apply 3 independent perturbations, P1, P2, P3, on each node of a network, allowing a relaxation to a new steady state. For example, we inhibit the activity of node 1, and we measure the variation of the activity of the other nodes. And thanks to the 3 independent perturbations, the global response matrix G contains the set of the experimental variation of the activity of every node. And we can demonstrate that the connectivity matrix R is a function of J minus 1. An example is given on the right side of this slide. It's a Phrygian network involved in breast cancer with RIP, LCOR, and luciferase are genes, and the independent perturbation are LcRNA. The baseline condition is under estradiol stimulation, and the activity of gen X as phosphorylation measures. And the connectivity matrix is given above. For the regressive approach, the experimental design is the same as the previous one. And thanks to the Taylor development, the variation of each node X1, X2, and X3 is a multiple linear regression of the other nodes. For example, for the node 1, the variation of node X1 is a combination of X2 and X3. The connectivity coefficient are the parameters of the regressions. And to obtain these particular coefficients, we delete from the J matrix the data associated with row 1 and the column 1. So we get a linear system 2 for 2, and the solution of it are the connectivity coefficient R1.2 and R1.3. So in this example, we can see that the regressive approach consists in solving 3 independent problems. We apply the regressive approach and classical MRI approach for a complex 6-module map kinase network. The dynamic of a system is composed of 12 fractional function YA, and the system is non-linear in relation with the different parameters, which are Michaelis constants and also the maximal speed of reactions. Baseline state is given by initial concentration at t equals 0, and we study the behavior for 6 modules in bisphosphorylated and not phosphorylated for the 6 modules. The steady state is evaluated with the air procedures multi-route. The exact solution of the system is a sparse network, and the associated connectivity matrix is given table B. We have got the exact solution using a tool of formal derivative, which is derived in if you use R software. Table A and C are the connectivity matrices got by MRA when using a set of independent perturbation with an increase or a decrease of 50%. So these are very important things. We can notice that the computed connectivity matrix given in table A and C are not sparse anyway. The error is not symmetric because of the non-linearity of the system. So if we examine more precisely the error function, in the left figure, we saw the evolution of a quadratic error between the theoretical connectivity matrix and the connectivity matrix calculated by MRA according to the intensity of the perturbations. In the right figure, we complexify the situation. We introduce biological data noise and free Gaussian noise with a standard deviation equal k multiply average x, where k is the variation coefficient with increasing values. And we see that a low perturbation corresponds to poor signal-to-noise ratio, and it is necessary to have a strong perturbation to get significant signals. Unfortunately, we are moving away from the exact solution because of a non-linearity. And a reasonable compromise is to take 50% perturbation. For this 50% perturbation, we show the impact of 2 different noises on the connectivity coefficients with a coefficient variation k equal 0.001 and k equal 0.005. The black confidence interval are obtained by bootstrap simulation on classic MRI with 100 samples. So we can see the large size of a confidence interval, and it's a well-known problem of classic MRY. The red and the blue confidence interval are obtained with only 3 and 5 technical replicates using classical regression theory. And the confidence interval are based on the pure error of the regression models. It is a very simple rule to use to detect significant edges. This rule is if the horizontal line does not cut the confidence interval, the associated connectivity coefficient is significant. So the corresponding edge is supposed to be exist. Now, we compare the benchmarks of different regression types to determine the existence of edges. We have digitalized the value of the connectivity coefficients, 0, -1 for an inhibition, and +1 for an activation. We define the sensibility as a ratio of a number of 2 positive plus 2 negative found in the network versus the real total number of 2 edges. The specificity is the number of 2 0 found versus the real number of 0 coefficients. TLR consists in putting a threshold on the quantities of the connectivity coefficients, and we take 25% of the maximum absolute value of connectivity coefficients. State-bar work is an iterative method. It consists in sorting the p-value associated with the connectivity coefficients and in deleting the last coefficient of a list if the sum of the residual squares is improved. And step forwards works on the other ways. We keep the best coefficient to reduce the residual variance of the regressions. And finally, it also consists in penalizing the norm L1 of the parameters of the regressions. So the result is given in the left table. We can see that the sensitivity decreases as the noise level increases, and the result of these different methods are quite similar for small-sized networks. It will be different from medium-sized networks. We are dealing with one last example using data from the DREAM Challenge 4. These are tangent networks on E. coli, 5 networks of 10 nodes and 5 networks of 100 nodes. Independent perturbations are knockdown and KO applied on each gen, and the network is considered to be Boolean. On the left side of this slide, an example of a network of tangent is given, and on the right, you can see the network formed by the TLR regressions. The number of unknown is 90 coefficients, and the red arrow indicates phase positives, and the green one indicates phase negative. So we find a total of 8 errors. The set of the result is summarized in the right table. The performance is quite similar for the small network, and we can see that MOS performance is sensitive to the choice of perturbation. It's not good for knockdown, but it's better for KO. For large networks, MOS performance is also poor. And conversely, regression methods like lasso, TLR, and STEP keep their performances for small and medium-sized networks. The sensitivity of least square estimation and TLR decreases with the size of a network, and conversely, the specificity improves. In conclusion, we can say that multilinear regression methods allow us to unravel biological network topology from dependent perturbation as classic MRI. Compared with classic MRI, they show the following advantages. With them, it's very easy to introduce redundant measurements, and thereby decreasing noise effect. Noise is inherent in physical measurements. And this subject is well known. So there exists a lot of calculation methods, and some of them fit well to MRI problem, notably concerning sparse connectivity matrices, which is this case is frequent with jet networks. So thank you for your attention.
you.
Thank you.
We have time for questions. Okay, I have one. So, how is the scaling of this method? What do you think? Where do you see limitations of how large these networks could?
Yes, the limitation is the steady state in this case. And we also see that the size of a network, in the case of Jen's network, is very important. So for small size, MAA, classic MAA is a good method, but we can see that for medium size network with, let's say, about 50 nodes, the noise is very important, and the noise deteriorated the solutions, and we obtain result like random result. And if you use a regressive approach, because it's a very well-known method which are developed, we have many methods for regression method, we can improve the performances of MRA.